Dear students, now I am going to discuss about an important topic. The topic is Lagrange's equation formation in classical mechanics. By Lagrange's equation, we can solve various types of complex equations easily. Various types of complex equations are applied in heat and thermodynamics, electricity, but with the help of Lagrange's equation, we can solve them easily. Before formation of Lagrange's equation, I want to mention a few points like constants, generalized coordinate, degrees of freedom. With the help of these few points, the Lagrange's equation formation can be done easily. First of all, I want to mention what is constant. If a particle moves in space and if we do not apply any force on the particle is known as free particle. But to form an equation, a restriction or condition is mandatory on a particle. This restriction or condition is known as constant. Without any concept of constant, any equation can be formed. In classical mechanics or in any type of mechanics, constants are classified in a various sections like holonomic, non-holonomic, cylindromic, rheonomic, conservative, non-conservative. But holonomic and non-holonomic are very important. Holonomic constants are written in the form of f function of r1, r2, r3 to t, that is t equal to time, and r1, r2 are position equal to 0. If constant or restriction or condition cannot be written in the holonomic form, the constant is known as non-holonomic. That is f, that is function r1 to rn, t is not equal to 0. Another important constant is rheonomic. Its example is simple pendulum. We all know that what is simple pendulum. In simple pendulum, a constant is applied which is known as rheonomic. Then I want to mention generalized coordinate. We are all know or aware about the Cartesian coordinate, but a new type of coordinate is known as generalized coordinate. Generalized coordinates are independent coordinates or specified or required to understand a system of configuration for a particular system of particles. So, in the formation of Lagrange's equation, generalized coordinates are required, and generalized coordinates are expressed by the symbol of q1, q2, q3, q4, etc. Now the topic is degrees of freedom. What is degrees of freedom? The number of independent or minimum independent coordinates. That is, before degrees of freedom, I have discussed about generalized coordinates. Generalized coordinates are independent coordinates, but degrees of freedom are number of minimum independent coordinates. The concept of degrees of freedom, generalized coordinates, constants are important to explain the Lagrange's equation. Simply, the number of degrees of freedom can be expressed by the equation f equal to 3n minus k, where k is the constant and n is the number of particles. Show a simple example for one atomic system. That is, the system consists one particle. The number of degrees of freedom is f equal to 3 into 1 minus 0. That is, no constant or restriction or condition is applied on the system. That is, the degrees of freedom is f equal to 3. Similarly, we can determine the degrees of freedom for 2 atomic, 3 atomic. If I take example of 3 atomic system, that is 1, 2, 3 particles. Restriction or condition is 1 or 2. That is, if the particles are arranged in this straight line, that is the two conditions or restrictions can be applied. These restrictions or conditions are known as degrees of freedom. That is, F equal to 3 into 2, sorry, 3 into 3 minus 2, that is 7. That degrees of freedom of the three particle system. That is 3 the number of particles and 2 is the restriction or condition. That is the system consisting 3 particles and are arranged in this form. The number of degrees of freedom is 7. But if the particles are arranged in this form, that is A equal to 3 to 3 minus 3, that is conditions or restrictions or degrees of freedom are 3, 1, 2, 3, that is degrees of freedom is 6. These are important to form the Lagrange equation. Now I want to mention what is Lagrangian. Actually, in classical mechanics, kinetic energy and potential energy are important. T is the kinetic energy and V is the potential energy. That is, kinetic energy minus potential energy is simply known as the Lagrangian. That is, the Lagrangian particle is known as the kinetic energy minus potential energy. And the Lagrange's equation for conservative system is written thus: d by dt of del L by del qk dot minus del L by del qk. Before I mentioned that q1, q2, q3 are known as journalist coordinate. That is, qk is the journalist coordinate and qk dot is the journalist velocity. If I take a simple example as a simple pendulum, because from beginning we are aware about the simple pendulum. This is a simple pendulum, and what is the theta angle at any instantaneous position. This theta is known as the journalist coordinate here. So if I apply this system to form the Lagrange's equation, we can directly put in this equation d by dt of del by del theta dot minus del by del theta equal to 0. And L, what is L? T minus B. That is T equal to half m L square theta dot square. And B equal to minus mgl cos theta. That is, if I apply L, that is T minus B in this equation, the Lagrange's equation will be in the form theta double dot plus z by L theta equal to 0. L is what is L? The L is the length of the string. This is the so much simple example of Lagrange's equation. Thus, this equation can be applied for many other examples. Compound pendulum. That is, for example, compound pendulum. What is compound pendulum? The compound pendulum is a body of an arbitrary size. That is, this is the compound pendulum arbitrary size, and it is the axis of rotation. Axis of rotation. With respect to this axis, the mass or the body or the system will move to and fro. And here theta is also the journalist coordinate. I am saying that the compound pendulum is of any arbitrary size. So I have taken the t equal to half I theta dot square, where I is the moment of inertia with respect to axis of rotation. So here I have not applied M like as a simple pendulum, because here the many particles are consisting in the system. So I have taken the moment of inertia I, and theta is the journalist coordinate. B is the minus mgl cos theta. Similarly, I have applied Lagrange's equation d by dt of del by del theta dot minus del L by del theta equal to 0. And mathematically, the compound pendulum will be in the form theta double dot plus M equal into G by L theta equal to 0, but theta is small angle, so sin theta. So here sin theta is neglected and only theta is calculated. These are the simple examples of Lagrange's equation. But utilization of Lagrange's equation can be done in electricity, magnetism, in various sections of physics. But Lagrange's equations are used in classical mechanics are elaborately. Double pendulum, but double pendulum that is consists of two pendulums where we need two JLS coordinates, equal pendulum that is three JLS coordinates. Harmonic oscillator. Harmonic oscillator. Of course, it is the example harmonic oscillator, isotopic oscillator, where we need JLS coordinate, and thus we can solve many complex equations, but easily with the help of Lagrange's equation. So let us stop the class for Lagrange's equation. Thank you.